Okay, my students, one question I received from you is to describe the plotting of magnetic field lines with a compass or iron fillings and the use of compass to determine the direction of the magnetic field. Look at this. Consider we have a bar magnet. This bar magnet has two poles, okay? First one is called North Pole and the second is called South Pole. Now, if I have a compass here, the compass has two ends. Number one, the head of this arrow is the North Pole of the compass, and the tail is what is the South Pole. And we know that different poles attract each other, and like poles repel each other. So this is the situation of the compass here. The correct situation of the compass here. What about if the compass is placed here? So this is the situation. No. This is the correct situation here. Because this is the North Pole of the compass and this is the South Pole of the compass. Okay? And you can draw compass anywhere. You can use this fact. This is the North Pole. This is the South Pole. Here and also here. Sorry. This is the compass, the correct situation, because this is here the South Pole and here is the North Pole and so on. Okay? Now, this will give us the direction of the magnetic field at any point. So this is the direction of the magnetic field. This is the direction of the magnetic field. This is the direction of the magnetic field. This is the direction of the magnetic field here, and so on. We know that the direction of magnetic field starts from the north and terminates to the south. Okay? Okay, another question that I received from you is to describe simple electric field patterns, especially about the conducting sphere. I already explained this in the classes. Consider you have a conducting sphere like this. And what do we mean by the electric field line? Electric field line is the path of a test charge. Test charge is always positive and small. So place the test charge here. It will repel. Here it will repel. Here it will repel. Here it will repel. So this is the pattern of the electric field line around the conducting sphere. It's same as point charge. It's same as point charge. Consider this point is called A and this point is called B. We can see in electric field intensity at A, okay, or force acting on any test charge placed at A is greater than the electric force acting on any test charge placed at B. Another question is to describe the use of voltmeters and ammeters, okay, with analog and digital, or what is the difference between analog and digital. Look at this. Any device with a pointer and scale, like this is 0, this is 1, this is 2, -1, -2, and this is a pointer. Any device like this is called analog, okay? Analog device. But if the ammeter is electronic, okay, this ammeter or this voltmeter is called digital. But the way you connect voltmeter or ammeter is the same in each cases for analog or digital voltmeters or ammeters. When you want to connect voltmeter to any element such as resistor, you should connect the voltmeter in parallel and ammeter in series. Okay? Another question I received is the use of equation of electrical energy. We know that power is energy per unit time. Make a cross multiply, so energy equal power multiplied by time. But we know that for any device or resistor, we have current I and we have voltage. The power is given by I multiplied by V, which is the voltage. Now we can use E equal, what is the power? Power equal IVT. So look at this simple circuit. Suppose you have electromotive force of a battery is 10 volts and you have a resistor here R with 2 ohm. Can you find I? Yes, I equal epsilon over R, which is 10 over 2, which is 5 ampere. Now, what is the potential difference or the voltage across the resistance? It's I multiplied by R, which is 5 ampere multiplied by 2 ohms, which is 10 volts. Okay? If you want to find the power dissipated through this resistor, you can use the formula P equal IV. So P equal I, which is what? 5, multiplied by the voltage across this resistor, it's 10. So the power is 50 watt. Now, what is the energy dissipated? Energy dissipated is PT. P is 50, and the time. When I say what is the energy dissipated across the resistor, I should mention the time in, for example, 3 seconds. So it's 50 multiplied by 3, so it's 150 joules. Or I can use the relation IVT and substitute this variable. I is 5, multiplied by V is 10, and the time is 3, so it's 150 joules.